Hello, good morning. Okay, we will start. We will solve the final exam. And please, if you have to go for the makeup, make sure that you know how to solve this properly. Okay, Bismillah. So, as usual, we read the question carefully and then we circle the right answer. After, of course, doing your calculation in your paper. The first question is an object, and I give you the mass of the object. This is m, 4.5. I give you the initial velocity, you see. So you can get the speed, the initial speed. And then I asked you, what is the net work done by the external force on the object to change its velocity to this? So this is the final velocity, v final. This is the initial velocity, v initial. So you know how to get the speed, right, from the velocity. The speed, v initial, is a magnitude of the velocity. Okay, great. So the question is to get the network. So I will use work kinetic energy theorem. You remember that change in kinetic energy is equal to the net work. Yeah? So if I want the network, I just calculate the change in kinetic energy. Half of m v final squared minus half of m v initial squared. So the network that I'm asking you is just half of the mass v final squared minus v initial squared. V final being the speed, final speed squared. So what is v final squared? V final squared is just 2 squared plus 8 squared, okay? I'm calculating the magnitude and I'm taking the square. So this is a v final squared. What is v initial squared? V initial squared is the speed squared. So basically it will be 5 squared minus 3 squared. So final answer is half 4.5, which is a mass, you do the calculation and E is the right answer. I hope it's clear. Work kinetic energy theorem. Great. Next problem, question 2. So I have a block and the block has a mass m, which is 8 kilograms. Push up an incline, 35-degree incline plane with a force parallel to the incline plane. So let's draw. This is my incline plane, and this angle theta is equal to 35 degrees. And I have the block. So here is a block. And I have a force which is parallel to the inclined plane. I did not say parallel to the horizontal. I said parallel to the inclined plane. So the force is like this. So this is F. The velocity of the block is constant. Well, velocity constant, meaning acceleration is 0. The derivative of velocity with respect to time. Acceleration being 0, meaning net force is 0. So the velocity of the block is constant, and the coefficient of kinetic friction between the block and the plane is 0.47. I give you mu k, 0.47. Find the magnitude of the force F. Okay, great. First, I will do a free body diagram. Let me take a blue pen, free body diagram on my block. So the system is my block of mass M. That's the system of study. Free body diagram, the first force is this F. We already drew it. Then we have the gravitational force, which is a weight. Fg. Then I have the normal force, normal to the incline. And I call it Fn. You can call it N if you want. Then we will have the frictional force, Fk. And Fk is opposing the motion. So you see here the velocity is in this direction and it's constant. Don't forget the acceleration is 0. Okay, so that's my free body diagram. Let me choose my x-axis and my y-axis. Of course, I will choose this to be my x-axis and this to be my y-axis, the normal to the incline. So let me use Newton's second law or Newton's first law because acceleration is 0. Basically, we'll have F plus the gravitational force plus the normal force plus the frictional force is equal to 0. Let me project along x. And of course, also I will project along y. So let me project this Newton's second law or Newton's first law, Newton's law along x and y. Great. So I project along x. The force along x is just plus F. You project this guy along the inclined plane, plus F. Gravitational force along x, the angle theta is coming here. So this is what I need. And again, as usual, so it's plus. It's minus mg sine theta. Okay. Fn along x is just 0. And Fk along x is minus Fk. And this is 0. Along y, you will just have basically Fn is equal to mg cosine theta. This component of the force, gravitational force, is equal to the normal force. So if I combine both equations, I will have that F is equal to mg sine theta, don't forget it, plus Fk. But remember, Fk is mu k at n, but Fn is mg cosine theta. Remember, Fk is mu k n, and Fn is just mg cosine theta. Bottom line, the force that I'm looking for is mg sine theta plus mu k cosine theta. You put the numbers. Here you see the m, I call it capital M. Right, so capital M or small m, it's the same, 8 kilograms. You do the calculation and you will get a force of 75 Newton. Next. So now we look at this problem, question 3. You read it carefully. I give you the mass. So mass, you put it in kilogram, 0.025 kilogram. I give you the maximum tension, 54 Newton. The ball rotates in a horizontal circle, and I give you the radius 15 centimeters. So 15 centimeters, 0.15 meters. Of course, on a frictionless plane, question what's the maximum speed before the string breaks. So here you know that the tension force will play the role of the centripetal force. So it should be equal to mv squared over the radius r. So the maximum tension, Tmax, will give you the maximum speed. So that means if I want the maximum speed, Vmax, I have to take the square root of Tmax. I multiply by the radius, and I divide by the mass. Let's put the numbers. Square root of 54, maximum tension, times the radius 0.15, times the mass, 0.025, and this gives you a maximum speed of 18 meters per second. Classic. Great. Let's look at the next problem. Question number 4. You read it carefully. Okay. And then you solve it. So I have this block and I give it an initial speed, and the initial speed is 8 meters per second. So it goes along this track here, which is frictionless. And then it climbs this height h, and I give you the height h, 2.1 meters. And after it reaches this height h, goes along a horizontal, and then here I have friction, and I give you mu k, which is 0.4. And the question I'm asking you is, what's the distance before I stop? So when I stop here, the V final will be 0. I started with an initial speed, which is 8 meters per second. And I end up with a final speed, which is 0. And along this journey, I have gone through a difference of height. And then I went through a friction road, a rough road. That's what I said here, a rough surface. The question is, I want the distance I will travel on the rough road before I stop. Okay, great. All what you have to do is to use engine mechanical energy is equal to the work of the friction. Okay. The change in mechanical energy is equal to the work of the friction. If the friction was 0, you will have delta E is 0, conservation of mechanical energy. Here, because there is friction, I have dissipation. So basically, engine mechanical energy is equal to the work of the friction. So I have to identify my initial state. This is my initial state. And I'm here. So this is the initial state. And here, what is the mechanical energy? Mechanical energy initial. Let me take the red one. Is equal to kinetic energy initial plus gravitational potential energy initial. So we don't have spring here. So this is nothing but half V0 squared, V0 being 8 meters per second. And now for UG, I'll take this as my reference. So basically, this is my reference. Y is equal to 0 here. So meaning UG is equal to 0 on this reference here. So UG initially is just 0. What is my mechanical energy final? E final is kinetic energy final plus UG final. So what is kinetic energy final? My speed, I will stop, speed is 0. So K final is 0. What is UG final? I'm at this height H. It's plus mgh above my reference. So E final minus E initial is basically mgh minus half mv0 squared. And this has to be equal to the work of the friction along B, which is a flat surface. So the work of the friction, you remember, will be minus FKD. So minus, what is Fk, is mu k Fn d, but it's flat. So Fn is mg. It's minus mu k mgd. Now, if I want B, I'll just take this and I divide by this. Simple. So D is half. And as you see here first, of course, it doesn't depend on M. Or that's why I did not give you the mass, okay, in the question 4. Okay, the mass will simplify. I have on my right-hand side the mass, on the left-hand side the mass, so it will simplify. So D is equal to half V0 squared divided by mu k G minus H divided by mu k. And this, when you do the calculation, you know everything. You do the calculation, you will have an answer of 2.9. Okay. So this gives you 2.9 meters. Great. Next. I have a box which is initially at rest, pulled across a horizontal rough surface, and I give you mu k 0.3 by a force 80 Newton directed 25 degrees above the horizontal. I could have made it below the horizontal, but here I chose to make it above the horizontal. Question: find the box final speed after it has moved by 20 meters. Let's draw the problem. This is my horizontal surface. Let's assume that I started here. And then I ended up here. So the displacement here is d. So if x initial is 0, x final is equal to d, which is 20 meters. And the displacement is along the horizontal. Let me draw a free body diagram on my plot. So I have my box, 25 kilogram box, meaning I have the weight, gravitational force, downward with a magnitude mg. I have the normal force, Fn. Well, it's moving. I have the frictional force, Fk, which is opposing the motion. And then I will have my pulling force, which is F. Let me draw it like this. And it's equal to 80 Newton. And the direction is theta, which is 25 degrees above the horizontal. Great. So I started from rest. So V initial is 0. Question is, what is V final if I moved by 20 meters? We have solved many problems like this. It's a classic, and you should know how to solve it. Okay, I can use different, let's say, tools. But here, let me choose either work kinetic energy theorem, delta K is equal to network, or I can choose, if I want, change in mechanical energy is equal to the work of the friction. You pick, or you can use also constant acceleration if you want. So, but these are best, okay, these two. So which one do you want? Let's use work kinetic energy theorem. Delta K, which is K final, half M V final squared, minus K initial, which is 0. I started at 0, is equal to the network. Network is sum of all the works, meaning I need the work of F, which is this pulling force here, along this displacement D. I need the work of the gravitational force. I need the work of the normal force. Then I need the work of the frictional force. First of all, we can say that the work of the gravitational force is 0. Because as you see, the gravitational force is making 90 degrees with the displacement. The work of the normal force is also 0 for the same reason. F G is normal to the displacement. Fn is also normal to the displacement. So the work of these two forces is 0. So actually what I need to calculate is the work of the constant force, the pulling force. So it is the work of the pulling force, just F dot D, which is Fd cosine theta. So let me write it down here. F, and I know F is 80, D, which is 20, cosine theta, which is cosine 25 degrees. I can calculate. Great. Minus, plus work of friction. Now you will tell me what the work of the friction. Interesting. So the work of the friction is minus Fkd. You all agree with that? D and Fk are making 180 degree between them, so work of friction is minus Fkd. It's minus mu k Fn d. Now what is Fn? Fn is not mg. Okay? So here you have to be extremely careful. You use Newton's second law on the y-axis. And if you do that, you find that Fn plus F sine theta is equal to mg. Basically, Fn is mg minus F sine theta. Okay? Because this force here has a component along y. Okay? So you have, many students will say, oh, Fn is equal to mg. No. You have to take into account the vertical component of F. In other words, I know everything now. Let me just write it in a nice way. I will have F E cosine theta. Work of the frictional force is minus mu k Fn d. But instead of Fn, I will write mg minus F sine theta. So that's Fn mu k Fn d. And then I write my d here. And this has to be equal to half mv final squared. So I know F, I know d, I know cosine theta. I know mu k. Where is mu k? It's given, 0.3. I know mg, I know F sine theta, I know d, I know m. My only unknown is v final squared. So you can write an expression with v final squared, which is square root of 2 divided by m, and then multiply by this. Don't make a mistake, okay? And then you multiply. Write the expression by yourself, because it will come back in the makeup exam. But it's a surprise. Don't tell anyone. Anyway, I hope you will learn the lesson and make sure that this type of mistake doesn't happen to you again. You do the calculation and you'll find 3.8 meters per second. Good job. I think most of you got it right, and I'm happy about that. Next. So for this answer is 3.8 meters per second. Next, let's look at a helicopter. Read the question carefully, okay? If the man, so this is the weight of the man, this is the mass of the man. This is a man, and you will have mg downward. And he's lifted by a helicopter by the means of a cable, and the cable has a tension. Okay? And the acceleration of the man is 1 meters per second upward. Acceleration is this, 1 meters per second upward. And then the man has moved up. I said it here. 12 meters vertically upward. So it's 12 meters. This is D, okay? The displacement upward. And the question I'm asking, how much work is done on the man by the tension? I want the work of the tension. Well, the work of the tension is a constant force here. It's tension dot displacement. Tension displacement cosine 0, which is just tension dot displacement. I know the displacement is 12 meters, but what is the tension? I can know it using Newton's second law. Tension plus gravitational force is equal to ma. If I project along the y-axis, which is the only relevant direction here, I have tension minus mg is equal to ma, meaning tension is ma plus g. That's the tension, and I just plug it here. So the work of the tension is the mass of the man, the acceleration of the man, plus the gravitational acceleration times d. And I know everything. 80, acceleration 1, 9.8, and d is how many? 12. And you do it, and you get 10 kilojoule. That's the work of the tension. Great. Let's look at this problem. Read it carefully. We have an inclined plane again. The angle theta is 40 degrees. And the boy or the child is sliding down with a constant acceleration. It's a rough inclined plane. So if there was no friction, the acceleration of the boy, A, will be in magnitude g sine theta along the incline. Right? The acceleration is going down here. And in magnitude, it will be g sine theta. But there is friction. You have to take into account the friction. So you will remove minus mu k g cosine theta. We have shown this many times. Okay, you can use Newton's second law, and then you will find that this is the acceleration. Okay, I will not demonstrate it because we did it many times. So here I give you the magnitude of acceleration. So it's this. I give you this. I give you know this. You know this. You know this. You know this. My only unknown is mu k. Let's write mu k. So mu k will be, you just rewrite this, you will have tangent theta minus a divided by g, and then you will have here cosine theta. And you do the calculation, you will have 0.28. This is your answer. Yeah. So if I were you, I will re-demonstrate this. You know it already using Newton's second law. Question number 8. I give you the mass of the block. So it's dropped from an height h. Okay. I'm not asking you the height h here, but you will see what I'm asking you. Onto a vertical spring, and I give you the spring constant. Just before it hit the spring, the block kinetic energy is this. Oh, yeah, I made life easy for you. So just before it hits the spring, the block is here. This is just before it hit the spring. Its kinetic energy is equal to 6 joule. So it's arriving just before it hit the spring, 6 joule. Question is, what is the distance of maximum compression? So this is my initial state. My final state is now my block is compressed, maximum compression. I mean, my spring is compressed, maximum compression. And at maximum compression, the V final is 0. So this is my final state. Now I'm asking you, what is this distance of maximum compression? What is X? Okay. What is this distance of maximum compression? I want a distance, okay? So it should be positive because it's a distance. Okay, so let's write. So here we have a conservative system. So conservation of mechanical energy, delta E is 0, meaning E final minus E initial is equal to 0. What is E final? So let's write it down here. I'll write it with the pen, which is blue. So E final, this is my final state at maximum compression. E final will be equal to kinetic energy final plus UG final, which is the gravitational potential energy final, plus US final. So the kinetic energy final is 0. So at maximum compression, V final is 0. The block will stop momentarily. What is UG final? Okay, I will take a reference because for gravitational potential energy, I need a reference. So I will take the reference to be here. Y equals 0 here. So UG final is 0. Meaning, what is UG initial? UG initial is mgx. Okay, above my reference. or my ground. Okay, this is X. So UG initial is 0. So our K final is 0. UG final, UG final is 0. UG initial is MGX. K final is 0 here. UG final is 0. What is US final? It's compressed. So it's half KX squared. So my E final is half KX squared. The rest are 0. Kinetic energy final is 0. Gravitational potential energy final is 0. I have only string potential energy there at final state. Now in my initial state here, so E initial will be K initial, which is 6, plus UG initial, which is MGX, plus US initial, which is 0. So basically I will have 6 plus MGX plus 0. Why my spring potential energy is 0? Because it's relaxed. Okay, great. So minus E initial, which is minus MGX, minus 6, which is equal to 0. So I have to solve this quadratic equation in order to get my distance of maximum compression. Let's put numbers. Half K. K is 500, so it will be half of 500, 250x squared, minus M, which is 2 times G, 9.8, so minus 19.6x minus 6 equal to 0. So this is what I have to solve. Well, you know how to solve this, okay? From high school, quadratic equation. So basically you have x12, which is minus b plus or minus square root of delta divided by 2a. This being a, this being b, and this being etc., etc. You know how to calculate a quadratic equation. You will have two solutions here. The first one is 0.1999 meters, which is just 0.2 meters. And the second one, x2, is negative, minus 0.12. So basically, which one should I choose? It's a distance. So forget about the first one. So the second one, forget about the second one, which is minus 0.12. You will get a distance of maximum compression, which is 20 centimeters. So that's the right answer, 20 centimeters. Next question. Let me choose a red color. So we have a single force, and I give you the magnitude of the single force, 20 Newton, and I give you the displacement. The question is, find the angle between the force and the displacement if the change in particles' kinetic energy is 100 joule. So, work kinetic energy theorem, delta K is network. Here, network, I only have one single force. Network is equal to work of the force. So what is the work of the force? It's a constant force. I did not say it explicitly, but you know that it's a constant force. Why? Because I'm asking you the angle. The magnitude is fixed, the angle is fixed. That's why I'm asking you the angle. So the force is a constant force, same magnitude, same direction. So constant force, work is F dot D, which is F, magnitude of F, magnitude of D, cosine the angle between F and D. I call it theta, and that's the angle that I want. So this work is equal to delta K, which is 100 joule. So this has to be equal to 100 joule. So that means this is the equation I have to use in order to get the angle. What is the magnitude of F? 20. What's the magnitude of D? Well, I know it in unit vector notation, so the magnitude of D is square root of 4 squared plus 5 squared. Cosine theta, and this has to be equal to 100. So cosine theta is 100 divided by 20, square root of 4 squared plus 5 squared. So if I want theta, you take cos inverse or arc cos. Okay, you do the calculation, the angle is 38.7 degrees. Let's solve the next problem, which is also a very interesting problem. So you have to draw in this problem. You read it carefully. And then you draw the problem. Okay, I guess you have read it carefully. So I give you the mass of the block, 6 kilograms. And this is my initial state. So the initial state is when I compress it by x, and x is equal to this. So I can calculate actually what is the initial mechanical energy. The initial mechanical energy is the initial kinetic energy, which is 0, plus the initial spring potential energy, which is half kx squared. And again, x is equal to 0.235. And you put it in meters. It's given here. And V initial, as we said, is 0. And what is UG initial? Well, I stay on the ground. So I will take the ground to be my reference. So there is no delta UG. UG will be remaining the same. Meaning basically UG initial is 0 as UG final is 0. I remain on the ground. So this is my initial mechanical energy. Now, if I release it from rest, it's pushed away. But remember that this has friction. It's pushed away, it will gain kinetic energy and it will stop eventually. When it stopped at a distance d from the initial position. So the total displacement is 0.5 meters. And when it stops, the final kinetic energy is 0. Now, what is E final, which is the final mechanical energy? It's kinetic energy, 0. Potential energy, which is 0. And spring potential energy, which is also 0. So here, if I want to solve my problem, I'll say that delta E, which is E final, minus E initial, is equal to work of the friction. E final is 0, E initial is half k x squared, and this has to be equal to the work of the friction, which is minus Fk, is minus mu k, Fn, which is mg, because it's flat here, times d. So, in other words, half k x squared is mu k mgd. I know everything here. My only unknown is k. So you can write k is mu k 0.3, m, what is m? 6, g 9.8, d, what is d here? I said it, 50 centimeters, you put it in meters, so 0.5 meters. Divided by half x squared. So what is x squared? X squared is x squared is 0.235 squared. Okay. You do the calculation, obviously, and you get a spring constant of 319 Newton per meter. Great. Next. Let's read the question carefully. I'll let you read it. So I went from point A, from point A to point B. So the displacement is AB. XB minus XA. And along Y, you will have YB minus YA. So the displacement is 3I hat plus 4J hat. Good. So this is the displacement in unit vector notation. And then I give you the force. The force in unit vector notation is 4, 2. For I hat, 2j hat. Displacement is in meter, of course. The force is in Newton, of course. So the net the net work or the work done by the force is F. So it will be a dot product 4, 2.3, 4. So 4 times 3 plus 2 times 4. This gives you 20. And this happened for a time interval of 2 seconds. I said it here. So the average power, P average, is equal to the net work, which is equal to the work of the force F divided by delta T. So it's 20 joule divided by 2 seconds. This gives you 10 watts. Next problem. So read the problem carefully. I give you the mass of the small block, which is this, and it's here at a point P. So it goes through a loop-the-loop. I have shown you loop-the-loop. So here, the radius is given, and it's equal to 8 centimeters. So the radius is 0.08 meters. The P data is this. Work done by the gravitational force on the block to go from point P to point Q. The work of the gravitational force to go from point P to point Q is equal to 4.2 joule. Knowing this data, calculate the height h. So you remember that work of gravitational force is minus change in gravitational potential energy. So this is minus mg delta y. So basically minus mg, but you remember what is delta y. So here I'm going from P to Q. Okay, so delta y will be yq minus yp. If I take the ground to be my reference, yq is equal to r and yp is equal to h. So delta y is r minus h. In other words, I have 4.2 joule is equal to mg h minus r. This is what I have to solve. So h will be equal to 4.2 divided by mg plus r. So I know everything here. M is 6, M is 0.9, G 9.8, R, you put it in SI units, 0.08 meters. So when you do that, you get 0.56 meters, which is 56 centimeters. Next. Okay, so here we have a pendulum. We discussed pendulum in class. Know that I did not give you a problem to solve a pendulum, but we discussed pendulum in class, so you know how to solve it. Great. So I give you the length of the pendulum, 0.5 meters. The mass, I did not give you the mass because the mass will cancel out, as you will see later. The initial speed of the pendulum is this, 20 meters per second. 2 meters per second when the angle theta is 30 degrees. What I want is the speed when the mass passes through the lowest position, meaning I want the speed here. In order to do that, You have to remember that the pendulum, if I neglect air resistance and all the frictions, the pendulum is a conservative system. So the tangent mechanical energy is 0. Delta E is 0. Okay? It's a conservative system. Conservative system. Okay, this means that E final, which is the mechanical energy at the lowest point, will be equal to E initial, which is the mechanical energy initial. Let's calculate both. So let's say this is my final position. I will draw this horizontal here. So my final position is the lowest point here. So this horizontal, I will take it as my reference. Y is equal to 0 at this horizontal here. So what is my mechanical energy final? Will be the kinetic energy final, half mv final squared, plus the UG final, but it's 0 because I took it as my reference. Now, what about the initial position? This is the initial position here. Let me draw the horizontal. Okay? The initial position is right here. So let's calculate E initial. Is the initial mechanical energy. It will be half mv initial squared, v initial being 2 meters per second, plus mgh, which is the gravitational potential energy. H being the difference of height between these two horizontals. We have shown that H is L 1 minus cosine theta. If you remember in class, we have demonstrated this formula. You can look at it again. If I want this H here, which is this difference of height, I have to take this length. What is this length here? This length is L. And I remove this length here. What is this length? This is L cosine theta. So this is L, and this is theta. So meaning this length here is L cosine theta. So the difference of height is L minus L cosine theta, as you used to do in high school, which gives you L 1 minus cosine theta. So mechanical energy final, which is half mv final squared, is equal to mechanical energy initial, which is half mv initial squared, plus mgh, which is mgl 1 minus cosine theta. And here you can simplify by m. You see that it doesn't depend on the mass, and you can get your v final squared. But I want v final, so it will be square root of v initial squared plus 2 times gl cos 1 minus cosine theta. When you do the calculation, okay, then you find an A of 2.3 meters per second. Just conservation of mechanical energy. Okay, question number 14. This we have solved it so many times. You can use directly the formula. Mu s is v squared divided by rg. V squared is equal to 90, but you put it in meters per second, divided by rg. What is rg? 150 meters, because I gave it to you in kilometers. You have to put it in meters, times g 9.8. You do the calculation and you get the mu s, which is the maximum static friction, or meaning the minimum coefficient of static friction before it slipped at this speed for a radius of this, and it's equal to 0.43. That's the answer. Okay, so we have demonstrated this formula so many times, but we will not do it again. Okay, great. So the answer is 0.43. In some problems, I will give you mu s, and I'll ask you what's the maximum speed to negotiate the curve without slipping. Okay? So you can get the maximum speed. You say V max will be square root of mu s Rg. Sometimes I will ask you what will be the minimum radius or the radius without slipping. Of course, if I give you the radius, I'll give you mu s and the maximum speed. And I will ask you the radius. Last question is this question here. And you read it carefully. I give you the mass of the box. It rests on a horizontal rough surface. And I give you mu s and mu k. So let's see, this is my rough horizontal surface. This is a box. It has a weight, which is mg, has a normal force, Fn. And then I apply a constant horizontal force of magnitude 60 Newton. Okay, I'm applying this horizontal force here, F, in magnitude is 60 Newton. Question, what is a box acceleration? Okay, so here I will have frictional force. Now the question is, will it be a static frictional force or a kinetic frictional force? That's the first question to ask yourself. In order to answer that question, I know that I have a horizontal force, F, which is 60 Newton, which is purely horizontal, which is equal to Fx. I have to calculate the maximum static friction, Fs max, which is mu s Fn, which is mu s mg, because remember that Fn here, the force here is horizontal, Fn is just mg. So I calculated 0.5 times m10 times g 9.8. And this gives you 49 Newton. So what do we notice? We notice that 60 Newton is bigger than 49 Newton. Basically, this force beats the maximum static friction. But that means the box will move. So Fs is not Fs. So this frictional force here will be a Fk, as we discussed in class so many times. So now, if it's an Fk, what is the acceleration? We use Newton's second law. We will say Newton's second law, F vector plus Fg vector plus Fn vector plus frictional force vector is mass times acceleration. Let's look at the x component of this. So I will have plus F plus 0 minus Fk is equal to ma. And along y, I will have Fn is mg. If I combine both, I'll have the acceleration is F minus Fk divided by m. So it's F60 minus Fk, which is minus mu k Fn divided by m, which is 10. So it's 60 minus mu k 0.4 Fn is mg. So 10 times 9.8 divided by 10. You do the calculation and you find an acceleration of this 2.1 meters per second squared. That's the answer. Okay. So if this Fs max was bigger than this F, the acceleration will be 0 because the box will not move. But here the pulling force, horizontal, is bigger than the maximum static friction, so the box will move and I will have a constant acceleration. And of course, the acceleration along y direction is 0. That's why I said just Fn is mg. So that was it. Okay, so go through it, especially when you have to go for the makeup exam. There will be no surprise in the makeup exam, but you have to know how to solve these questions. And I hope you know already. I wish you nothing but the best. And See you.